go. Okay, so atoms of the same element are always going to have the same number of protons. This is what we're referring to when we refer to the atomic number. You're going to notice once you start looking at your periodic table there, the atomic number is what it's organized by, right? And that atomic number directly corresponds to the symbol, doesn't it? So if you have either one of those pieces of information, atomic number or symbol, then you know the other, okay? Because if it has one proton, i.e. one atomic number, it is always what element? Hydrogen, right? If it has two, helium, okay? That's because it's that nucleus, the positively charged elements in that nucleus, protons, which cause all the other chemistry, okay? And everything else about that atom is caused by those little magnets in the middle that we call the nucleus, right? So, again, it's number of protons. We refer to that as the atomic number. Again, that is what indicates what element it is. That's what causes it to be that element, okay? Does it matter where it comes from in terms of if it's that element or not? Nope. Doesn't matter where it comes from.
I don't even understand what you mean by that.
So you can actually make elements.
Oh.
Yeah. So for example, carbon-14 is constantly made in the atmosphere.
Okay.
Okay. Most of the elements that were incorporated in were made through stars and decay from there. There's actually a few other sources, but we won't get into all that. Now, the number of protons gives the atom its unique properties, of course. So atomic number 6, carbon, is carbon because it has 6 protons in that nucleus. Okay? That's what makes it carbon. All right, so the atoms are usually considered neutral, i.e. no charge. They're neutral when you have the same numbers of electrons and protons. Okay? And that's what we typically consider the stereotypical atom, right? So if we're just talking about like carbon off the periodic table, that's neutral carbon, and it's going to have 6 electrons, 6 protons. Okay? That's because that's what makes it neutral. The carbons are going to contain 6 electrons to balance out these 6 protons. If we have 7 protons to balance that out, we need how many electrons? 7, right? Remember that electrons are negative, protons are positive, right? Okay, so this right here is actually an element. This right here is lithium, and this would be its nucleus right there. And then we have 3 electrons around it to balance out the positive charge. Okay, 3 protons, 3 electrons. All right, this one here is actually carbon. This is graphite ground up, like your pencil lead. And this one here has 6 protons, and it has 6 electrons to balance that out. Is this an accurate representation according to size? No, not at all, right? Okay, this nucleus here, oh my goodness. You may know what that is. Oh, wow. It really is. So this nucleus would be the size of a tennis ball. This right here would be a football field. Okay? If I actually gave you an accurate one, you wouldn't be able to see it. Right. Okay. So mass numbers. For anybody that's late, please let me know at the end and double check that I have that information, okay? So I can put you in the attendance. So mass numbers, that's going to be the number, that's the protons plus the neutrons, okay? Now, this is going to be the mass of that nucleus. So again, it's the protons plus neutrons that gives us a mass number. This is the symbolic notation and how you represent these different nuclei. And so right here we have the atomic symbol. Right here we have the atomic number. And this is going to be your mass number. Notice again that mass number is what? protons plus neutrons. So notice that atomic number is what? Protons. So if you take the difference between these, what do you get? Neutrons. Yeah. So quite nice and easy, right? Oftentimes you will see this atomic number left off. Oh my goodness, what will we ever do? Does it matter if we leave this off? No, carbon tells us that, doesn't it? So you look carbon up on the periodic table, its atomic number is 6. And so the carbon actually told you the atomic number as well, doesn't it? Okay. If you have a charge, you'd put the charge up here. There's nothing listed there, so that charge is 0. It's neutral. Okay. If it were negative, you'd have a negative symbol up here. If it was positive, you'd have a positive symbol. If it was positive 2, you'd 2 plus. Okay. And that's where that's listed. Okay. Now, you will notice that up on the periodic table, there's a few of them that basically make sense for this, for these mass numbers. So, for example, hydrogen is essentially 1, right? That makes sense. It has a proton, right? There you go. Nothing else. But you start looking at that periodic table, what do you notice about that periodic table? Chlorine. Have I mentioned a half proton or neutron? Does that make any sense? No, that doesn't make any sense, does it? How the heck do you get a half neutron or proton? No, do you? So what you're looking at there is these numbers on the periodic table. These are weighted averages. Okay? It's just like there is no such thing as a 0.1 person, right? But if you look at the average number of children in American households is 2.1, right? So there's not a 2.1 family. There's a tenth of a child got born. It's not going to work. So that is a weighted average, right? Just like your grades are weighted averages. Okay? And that's actually what you're seeing here. You're seeing the different isotopes is what that's called. Okay? Okay. This right here is determining the number of subatomic particles. It's just what I said before, spelled out into steps to make it longer to memorize. If you need it in clear steps. So let's talk more about isotopes. So atoms of the same element, these can have different numbers of neutrons. Remember, what makes it that element is the number of protons, right? If you have different numbers of protons, you have different elements. Different numbers of neutrons, it's still the same element. Okay? What that will affect is how stable the nucleus is, that number of neutrons. So, for example, you can have carbon 12, carbon 13, and carbon 14. So a carbon with the mass of 12, a carbon with the mass of 13, and a carbon with the mass of 14. Okay? Carbon 12 would have 6 protons, right? They all have 6 protons because they're carbon. This one's going to have 6 neutrons, right? This one's going to have 7. And then 8 neutrons. Okay? This one right here is radioactive, actually. It decays over time. Anybody ever heard of carbon dating? Guess what you use in carbon dating? Carbon 14. Yeah, breaks down over time. Okay? So when something dies, it stops taking in new carbon 14. It breaks down over time, and you can date how long since it's been dead. Neat, huh? Yeah, look at that. So again, those are called isotopes. We're going to have different mass numbers. When we're looking up at the periodic table, that's actually telling us the average masses of all carbons. If you just gathered like a million of them, that would give you the average mass for that mole of them. Okay? Okay, so again, that's isotopes, different mass numbers, different numbers of neutrons. All right. So again, the periodic table is telling us a weighted average of those, okay? It's kind of like the average number of kids in a household. There is no chlorine nucleus that is 35.45. Okay? That doesn't exist. Okay, so again, that would be the atomic mass. It's the average atomic mass weighted to all the isotopes of that element found naturally. Though some of these are not actually found naturally, so any numbers that are given are unnatural. You notice that down there, see where they're like not filled in on the periodic table, and they're like a hollow trace out. Can everybody see it? Okay, it's at the very bottom of the periodic table.
The outlines.
Yep. Notice the masses here. They don't have decimal places. That's because they're exact numbers. Because they made that atomic mass. That's it. So they don't occur naturally. Yeah, all of those ones are man-made. We've never encountered them naturally. Okay. Now keep in mind that this is not the universe. We have no way of knowing like what the average mass of anything would be for the universe. And in fact, these are what we have available to us. So for example, if we were to go to Mars and start colonizing Mars, we actually might end up with a periodic table of Mars. And that periodic table would have slightly different, very slightly different average weights on these atomic masses. Okay? Because you'd have slightly different isotopic ratios. It'd be very little difference, but it'd be there. Okay? All right. So this right here is, again, the isotopes for carbon. Notice, again, because our number of protons are the same, the number of electrons to be neutral is also the same, isn't it? Okay. Now, in terms of these isotopes, 99% of the carbon on the planet is carbon-12. Okay. That one is really loud. About 1% of the carbon on the planet is going to be carbon-13. Okay. And that's actually why, look up this carbon here. See how it's 1/100? That you see that 0.01? That's the carbon-13 showing up. Okay? That's what's creating that. And then you look down here, and it is like a 1 in a, I forget what it is, trillion, I think, if I remember correctly. Very, very small number is carbon-14. They're breaking down all the time. That's what we use for carbon dating. Okay. That does show up on that number, but very, very low. That's that 0.0008 number on that there. That's part of that. Though that's also electrons are showing up there. So that's also where the electrons will start showing up. Mm-hmm.
Is it true that when we're doing nuclear weapon testing, we really try to find new elements?
I can't hear.
Sorry, is it true that when we're doing like nuclear testing and stuff like that, like we would find new elements in the explosion?
We did actually, yes. We did find new elements. Most of them had been predicted before, but we had never actually found that element before. Since we found most of those as elements on the periodic table, but if you go over to uranium, you can actually start seeing where we kind of found new stuff. So, like for example, uranium was the first nuclear bombs, the non-hydrogen bomb, and that actually we did find neptunium. Yeah, and we encountered that because that's a neutron coming on here, and we made enough of it that it would be detectable. Though I don't think they found it in the actual explosions. They found it in the testing software. Yeah, so we would have generated. Also, another interesting thing is the waste from that process actually generated elements and isotopes we had never seen before. And if you were to look at like the largest concentration of wealth on the planet is actually the nuclear repository of nuclear waste in the United States. Because we've been building that up for decades. We put them in concrete sleeves and then they break down over time. And so it's made all these daughter isotopes. And for example, americium is incredibly expensive. So if we were to just go through and separate out the expensive isotopes in there, we could probably pay back the national debt. Yeah.
What would you do with it though? What did they do?
Sell them on the market.
For what purpose?
Fire detectors, like americium is used in fire detectors. Very tiny quantities, but
A fire detector?
yeah,
Do you
fire
mean-
detectors.
Do you mean like a smoke alarm?
Yeah, smoke alarms, fire detection
Yeah.
using smoke, uses a radioactive isotope that shoots out beta particles. Then the smoke captures it, interrupts the stream, and that's how you detect the smoke.
Interesting.
And so you guys don't realize this, but there's actually all these different radioisotopes all around you that are getting used constantly for all sorts of processes. And so it's actually kind of a fascinating thing that if you were to actually go through and separate these, not such a trivial process, by the way, but it would be a massive amount of money. Yeah, it's worth far more than Fort Knox. And they're just sitting around. Technically, anybody that could haul them away could haul them away, but they're in these giant concrete bunkers that are like 20 people linking their arms to surround it. So, yeah. Anyways, kind of an interesting thing. Since then we've made elements in different ways. Usually, what you do is you take a lead block, you take a radiation source that's shooting out protons or neutrons, usually, and you basically drill a hole in the lead block. So you reach the radiation source and make a little beam out of it, and then you put the nucleus in front of it you want to affect. Yeah. And that's how they do that in hospitals usually. And then there's, of course, like the CERN colliders. But those things take so much electricity to do that. Like we have made elements, the really heavy ones here. That's how we make those. But it's you're never getting a significant amount out of that. Yeah. Okay, so the energy given off spontaneously from a nucleus of an atom is called nuclear radiation. This is going to happen due to decay, due to the fact that that nucleus is going to be unstable. Okay, and that stability, that's determined by the ratio of protons to neutrons. Okay, so if you have too many neutrons or too few neutrons, you're going to end up with an unstable nucleus, and it's going to spontaneously decay over time. Now, these unstable atoms, these can radiate. This is why it's called radioactive. It literally gives off, well, first off, usually almost all of these give off radio waves. So if you bring like a stereo next to it, it'll actually pick that up and crackle and pop a bit. But it has to be fairly strong to really cause something you can hear. But they all do it to some degree. So again, these are going to emit radiation. And so they are literally radiating, active. Okay. So radiation is going to be a form of energy that we get from natural and human-made sources. 1896, Henry Becquerel got an exposure on a photographic plate in the dark. Did it by, he had a drawer that he used and put his photographic plates for doing various photos in. And he had a rock sample that was given to him. As it turns out, that rock sample had uranium in it. And so it caused all of his photographic plates to have those exposure spots on them, despite the fact they were in a dark drawer. And he took out his photographic plates, tried to use them, and he's like, what the hell's going on? And luckily he went, oh, wow, I wonder if it's that rock. That is. I think my wire's going out. Okay. And so it's kind of an interesting and fun story. A lot of discoveries get made out of that. It's sort of an accident, but the person's ready to like look into it, right? And ready to actually think about it. Okay. Lots of accidents get made and no discoveries happen because the person doesn't know anything and doesn't do anything about it. Yeah. So most naturally occurring isotopes are going to have a stable nucleus and are not radioactive. This is one of the reasons why they're naturally occurring. Okay. If they're all radioactive or they're so radioactive that they decay really fast, we never find them, right? And so that's why we have up to a certain mass and it just stops having naturally occurring isotopes. So isotopes that are not stable, they're going to become stable by spontaneously emitting radiation from the nucleus. That process of emitting radiation is called radioactive decay. And so all of those ones that are past lead, essentially, those are all radioactive to some degree. Though some of them, like uranium-238, are actually not that radioactive. They decay really slowly. Okay. And so we can find them in nature. But everything after lead essentially is radioactive. They're all going to do radioactive decay pathways to get down the periodic table to lead. All right. These are radioisotopes, these isotopes that emit radiation. They're naturally occurring radioisotopes. These can be mined from the earth. We typically have to prepare them in laboratories to concentrate them to large enough quantities that you can actually detect and really use them in any significant amounts. All isotopes of elements with atomic numbers 83 and higher are radioactive. So the easy way to kind of remember that is the switch off is lead. Okay. And that's what most of them break down to.
What's the symbol for lead?
PB.
That's what I thought.
Yep.
Why? Is it Latin?
It is. Yeah, and that's where the
Or-
plumbing comes from. Like the word plumbing comes from lead pipes.
So what is the actual Latin?
Plum something?
Something. Okay.
Yeah.
Something.
Yeah. It's been a while since I bothered looking that up. Pluribus, plumbus, yeah, something like that. You can look it up sometime. Let me know. Okay. So some lower elements also have radioisotopes, by the way. Like I had mentioned, carbon-14, right? That's a radioisotope of carbon. Many of the lower elements actually do have a radioactive isotope. That's possible. Many of them are so radioactive that you'll never see them, though. Okay, so they get made in like stars and in the upper atmosphere, and they break down right away. Yeah. Okay. These are the forms of radiation that are going to happen in these radioactive decays. And so we have the alpha particles. This is alpha decay. It's going to shoot off an alpha particle from the nucleus. We can denote that with an alpha, or a helium nucleus. Though keep in mind that these are going to be moving very fast. They're like a 0.1 speed of light sort of thing, which is really fast. Okay? Like that's crazy fast. If you had anything with any real mass, like a gram, moving 0.1 the speed of light, it would like blow up the building. Okay? Just boom, gone. So extremely high energy. It's going to have a 2+ charge because it's moving so fast. It's going to get ejected and never have a chance to pick up any electrons. Okay. Beta particles are going to be a capital beta symbol, and those are going to have a mass of 0. It's electron moving very, very fast again. This moves actually much faster than the alpha nucleus. And it'll have a -1 charge because it's an electron. Okay. Gamma, these are, anybody ever heard of gamma rays? Hawk Smash? Is that where you guys all heard it? Yeah? No? Okay. So gamma rays, these are actually, the easy way to kind of think about this is that this process is kind of like having an unstable house, right? So you have an unstable nucleus. It's going to collapse down, okay? When an unstable house collapses down, what do you hear? Sound, right? So when an unstable nucleus collapses down, what you get is you get radiation that's in the electromagnetic spectrum, i.e. light, okay? And so this is the highest energy of the electromagnetic spectrum, gamma rays, right? It's higher energy than X-rays, and those are way higher energy than like radio waves, okay? And so this is kind of like the sound of your nucleus collapsing. It's a release of energy. These right here are going to be called positrons. Anybody ever heard of antimatter before? Okay. So positrons are antimatter. All antimatter is it's just matter with the opposite charge. Okay. And so it's a positively charged electron or positron. And so it's going to be an electron essentially, but it has a positive one charge, not a negative one charge. Okay. If a positron and electron were ever to collide, and they do collide, that happens, they release gamma rays. So they release energy and annihilate each other, cease to exist. Okay. Neutrons are going to be neutrons. So you shoot off neutrons. For example, uranium, when it decays, it shoots off 3 neutrons typically. Okay. That's actually how nuclear reactions occur, and we'll see that in just a bit. And that has a charge of 0. Keep in mind that these neutrons are being shot out at fractions of the speed of light. Okay? So if they hit another nucleus, they're going to be like shooting something with something incredibly high energy, right? And so they can do things like actually join the nucleus when they hit them and cause your nucleus to change. Okay? And they can cause it to break apart as well.
So is this what quasars are emitting?
Yes.
All of them, or is it just like gamma?
So technically they are emitting all of them. In fact, our sun is emitting all of them as well. Okay. But the gamma rays on a quasar is a lot higher than a normal sun. And so they're more detectable. Supernovas cause actually gamma ray bursts, and which is like this terrifying thing that causes like beams of gamma rays to just travel through space for long distances. And if something like that happens and it happens to head towards Earth and it's not far enough away, we'll just like poof, gone. Like it'll just
magnetosphere wouldn't protect us from
not
it.
at
They
all.
could just wipe it out.
Yep.
Wow.
Yeah, if it's not far enough away. If it's far enough away, it will ionize a portion of the Earth's atmosphere, and it will still cause most of us to die. But some of us might survive. And if it's far enough, even further away, we'll have lesser effects. But it would actually take out, like, there's distances that this would cause the complete collapse of all society.
So
Because it would destroy
what about,
communications
like, our
for
solar
years.
Flares?
Mhm.
So our solar flares is just gamma radiation.
The solar flares are okay. So what happens in a solar flare is actually you have bursts of material coming out.
Okay.
Yeah. Now it does have some gamma ray release because our sun is just a giant nuclear reactor. Okay. It's doing mostly fusions, but it goes up to iron in terms of fusions, and it does make unstable nuclei within there, and so it has decays that happen too. And so technically a sun does all of these things. Yeah. But like the positrons don't make it anywhere because there's electrons zooming around everywhere.
Okay.
And so they just get annihilated. You get gamma bursts, little tiny ones all over the place. And so we do have gamma rays coming out. Our magnetosphere and our atmosphere are protecting us from basically all that. Though there are some high energy gamma rays that do make it through. It sometimes ejects neutrons, and so neutrons can get ejected that actually will penetrate part of the way through buildings and all the way through some buildings, and like part of the way through the Earth's crust. This is actually what creates carbon-14, by the way. Like our atmosphere gets hit by this all the time, and it actually causes nitrogens to go to the nitrogen-14 and decay. Yeah. And that's what makes those radioactive isotopes. Yeah. And so like the beta doesn't really go anywhere. The alphas don't really go anywhere. They cause like heliums and hydrogens and the going up to iron, but they don't actually go very far from the sun usually. A few of them do, but not much. So anyways, it gets a little complicated because you have a lot of stuff going on a star. But yeah, you can have like neutron bursts off of quasars and stuff because they're more unstable stars. And so a lot of the things that we don't normally get hit by from our star, you could get hit by from a quasar because it's jetting things out. Yeah. So kind of interesting. There's actually a lot of gamma radiation comes off of like black holes, by the way. Yeah. Because it squeezes things as they come down. Anyways, so there's some really crazy stuff. If you guys want to talk about that a lot, that's actually done a lot in like inorganic chemistry. But that's a 400 level chemistry. So, Okay, so this is alpha particle again. It's a helium nucleus, but remember it's going at a tremendous speed. Okay. Now keep in mind that even though it's going at tremendous speed, it has so little mass that you can get hit by these all day, and you are hit by these all day, and it doesn't really do much to you. Okay. Because yeah, it may annihilate a dead skin cell, but you have 7 layers of dead skin cell on you. You don't care. Okay. Again, 2 protons, no electrons, atomic mass 4, so 2 neutrons, right? Okay, this beta particle, and again, it's going to be an electron. Again, very fast moving electron, though. Okay, shot out at tremendous speed. But remember, electrons have almost no mass, right? We have a 0 for our mass number here, so usually doesn't accomplish a lot. Okay. Gamma rays, again, these are very high energy radiation that's emitted throughout the process of radioactive decay. Doesn't contain any particles. These would be called photons, but the duality of light is a bit of an advanced topic, and we'll kind of avoid it here, okay? Because we got stuff that you guys would probably like to know, and I don't think most of you care about that, but we'll cover it in just a minute. Gamma rays are going to be released from non-stable nucleus, so rearranges to a more stable state. So typically what happens is you like emit an alpha particle, and then you'll be a high energy version of the daughter. And then what will happen is that will collapse down into a more stable structure and emit gamma rays. Okay? And that's typically how gamma rays decays happen. You'll see one of them in just a bit when we get to nuclear reactions. Gamma rays is the Greek letter gamma right there. Gamma rays are the higher energy version. X-rays are a lower energy. And so you may remember and have seen X-rays before. So they accomplish pretty similar stuff whenever they hit an atom, which is to say that they ionize those atoms. Though gamma rays are so high energy, so fast that they kind of blast things apart if they actually get absorbed. So this is a positron. That is antimatter. You are actually, who here's had a PET scan? Okay. You ever hear any sci-fi and they're like shooting antimatter beams at people? Guess what? You've been shot with an antimatter beam. That's what they do when they do a PET scan. So they're shooting you with an antimatter beam. The P in PET scan is positron. Positron emission tomography. By the way, a tomography is a type of scan, and all the different medical scans all end with types of scans. And so technically your doctor is saying scan all the time. So when you say PET scan, they're going scan. And whenever you say PIN number, personal identification number, so you're saying number. Yep. Give me your number. So I know it's silly. Yeah. So you can kind of make fun of your doctor friends if you ever want. Okay, scan. All right. So the neutron has no charge, represented by a neutron, obviously. Again, these are going to be shot out at tremendous speed. Notice that if they're aimed at a radioisotope, they can actually add to the nucleus and cause radioactive decay. And so, for example, everybody's heard of a nuclear reactor or a nuclear bomb, right? We're talking about nuclear bombs. Okay, so that uses uranium-238. If you were to take a uranium atom, its decay is going to release 3 neutrons like a little shotgun burst. Okay? And what's going to happen is, what happens if you have a bunch of uranium atoms around that one? Well, those are going to get hit, aren't they? And then they'll release 3 neutrons. If you have more around them, they're going to also do that, aren't they? And so what ends up happening is if you get a critical threshold, okay, critical mass is what it's called, of uranium atoms all in one spot, they're actually going to go nuclear, which is nuclear bomb, okay?
And that's where we get the term chain reaction from.
Exactly. That's exactly it. That's a chain reaction.
Mm-hmm.
Now, if you very carefully ride that line and you don't actually let it go past the critical threshold, but you keep it going, chain reaction all the time. That's a power plant. So that's a nuclear power plant. Okay. And if you don't let it get to that critical threshold, it will eventually sort of like just go at its natural decay rate, which we'll talk about in a little bit. It's called a half-life, but it will release heat. And so that's how we do like the nuclear powered satellites, okay, or probes that we send to other planets. We use that little heat source to give us energy. Okay. Interesting little factoid: NASA is one of the largest radiation emitters to ever hit the planet. Did you know that? So NASA launched a probe back in like the 1980s, and they messed up and blew up the probe in the atmosphere and released a bunch of uranium all throughout the planet, right into the atmosphere. Most of it has kind of worked its way to the ground at this point, but they actually are one of the largest single increases of radiation on the planet. They're up there with Fukushima. So, whoops. NASA. Geez, this class, I feel like kind of bad. I kind of pick on NASA in this class, don't I? Like exposing all their mess ups. Sorry. Sorry, NASA. Biological effects of radiation. So radioactive emission is going to contain a lot of energy. It will interact with atoms, whether they are living organisms or not. It doesn't really matter to radiation, of course. Alpha and beta particles, neutrons, positrons, gamma rays, and X-rays are all types of ionizing radiation, meaning when you're struck by them, it causes you to ionize. So your atoms and molecules become ionic, gain charges. And this, of course, is going to mean that they're going to react with whatever's next to them. Okay? So they do this in slightly different ways depending on which one we're talking about, by the way. So like beta particles straight up is just putting an extra electron over there. Neutrons, on the other hand, are going to break apart the nuclei that they hit. And positrons, on the other hand, are going to annihilate an electron, and you'll be down an electron. Gamma rays literally just launch the electron out of that molecule. Yeah. Okay, and so the loss of electrons in living cells, this is going to affect your cell's chemistry, and if it happens to be near your genetic material, you can have very long-reaching consequences. So this is how like nuclear radiation causes things like cancer. If you happen to cause ionization and it reacts with the correct spot on your genome, there's actually a range of spots on your genome that if it reacts and change, that will cause cancer. Okay. Okay. Anybody know what cancer is?
Missteps, mutations in our genes, just coded wrong.
Yeah, it's a wrong change in your genes makes your cell immortal, and your cell just tries to replicate over and over and over as fast as it can. Okay. Interestingly enough, it does actually make those cells immortal. So they will no longer take kill commands. They will outlive you if they're given nutrients. And that's how we make immortal cell lines. So like the cell lines that are studied in labs, those are just very selective cancers. Yeah. So, and there's one cell line that's outlived its person by over 30 years now. So, yeah, kind of creepy, right? Yeah. Yep. Anyways, they can sometimes not cause cancer, and we do have corrective mechanisms, but our mechanisms are not quite as good as some other organisms. So that's why cancer is a big problem in humans, though we have a pretty long lifetime compared to a lot of other organisms. So the biological effects of radiation again, radiation of higher energy can penetrate further into the tissue, affecting the cells located deeper in the body. These cells that are deeper in the body typically are more important cells and will cause more diverse problems. One of the big ones to consider is like your bone marrow. That's why cancers like the bone marrow are incredibly difficult to deal with, right? Very dangerous. Okay. That's like if you were to select one spot, you really don't want to get cancer, it's the bone marrow. Yeah.
Well, that it makes our blood, so
it makes our blood, stem cells. You get cancer in your bone marrow, life is difficult. Um, persons that work with radioactive materials typically wear heavy lab coats, lab glasses, gloves, stand behind plastic or lead shields. They're trying to isolate themselves from that radiation. Depends on the decay that you're experiencing, what protections are most effective. But you'll notice one of the key things, they always try to not breathe it in, okay? Not take it into their bodies. Now, did I talk about the one of the inventors of the nuclear reactor and his demo to prove that nuclear radiation is safe? No? Okay. So after 3 Mile Island, the government and people just went crazy on nuclear radiation. We increased the number of regulations around nuclear radiation by over 50 times within 3 years. And after that, we have never successfully made large-scale nuclear reactors in the United States. We've destroyed the entire industry. And the reason for that is we put a no lower limit on our nuclear safety. And so let's say that today somebody accidentally drops one little tiny piece of uranium. Boop. Okay. So within a radius around that, any radiation source, no matter how small, has to be contained. Do you know who's radioactive? What is radioactive? Us. We're radioactive. So technically, you would be nuclear waste that they have to dispose of. The sun is radioactive. So that is also a nuclear waste that has to be dealt with. Luckily, they usually kind of like have reason, but it gets insane once you start doing no lower limit to your radiation safety. And as you'll see in a bit, that is absolutely moronic. There absolutely is a lower limit to radiation safety. And it was actually proven very, very graphically by one of the inventors of a nuclear reactor. So he actually took a piece of uranium, a little bead of uranium, and he swallowed it and passed it through him, and eventually he would have pooped it out. But that, you can do that. It's not a problem at all. Okay? Uranium, if it's very, very pure uranium, is actually not digestible, won't enter your blood system. And for the amount of time it's passing through you, you're not going to get any particular radiation dose. He lived a full, long life, never had any issues with cancer. Okay? The scientists that worked on the original nuclear weapons program, they used to carry plutonium in their pockets. And again, as long as you understand what you're working with and are careful with it, you can get away with that stuff. They lived full, long lives. They never had any issues with radiation. They never had any issues with cancer. Okay? Because they knew what they were doing and they knew what limitations and what safety protocols they needed. Okay? I would not recommend doing that. Like, it's very easy to make mistakes, right? We all make mistakes. If he had swallowed that uranium and it had too much uranium oxide on it, and his stomach acid would have pulled the uranium into his blood system, and he would have died a very painful death. Or at the very least had poisoning on the order of like lead poisoning. Okay? So that was actually a dangerous thing to do, but he made a very pure sample of uranium and did that, knowing exactly what he was doing. Okay? So don't go swallowing uranium yellow cake or something and be like, I'm going to be okay. Dr. Dawson said I was okay. You're going to die. Because uranium yellow cake is oxidized uranium and it's your stomach acid release uranium into your blood. So don't do that. Okay. But again, if you know what you're working with, you can take the proper precautions. People who routinely work with radioactive materials or x-rays are going to use film badges to monitor total exposure. Some of you might actually do this. They're the lab techs in hospitals. They actually make pretty good money. It's a good job. You don't have to have a huge amount of chemistry either. You might want to look into it if you have any interest. But make great money too. And they'll work around radiation sources. They'll make the different isotopes for testing in hospitals. And one of the things that I really need to warn everybody about, if you work with radiation sources, make sure that you change your film badge when you're supposed to. people get lazy about it after they work in the field for like a couple of years. They don't change those badges. And what happens is they either never change color ever, they stop just working completely, and then you don't know if you ever get exposed to them or not. Okay? Or they change completely to, oh my God, I'm going to be dead all like at once. And so one day your badge will just go blank. And you'll be like, oh my God, I'm going to die. And it's because the film is too old, right? So, like, follow the procedures, guys. They're there for a reason. I know it gets tiring, but okay. So this is some of the biological effect. Remember that first off, radiation on the outside of you has a much different effect than radiation inside of you. Okay? So like an alpha particle, it's actually blocked by your skin. You have 7 layers of dead skin. It's not going to do anything as long as it's not inside of you, okay? Not a big issue. You could take a piece of paper, put it in front of an alpha particles, and it's going to block it. Okay? There you go. Yeah. Now, alpha particles is something inside of you is going to have a greater effect. Still not like super horrific, but a much larger effect inside of you. If it happens to have the atom inside of your cell next to your nucleus, it's going to have a big effect. That's going to be where things get really dangerous. Okay? Now, a beta, this will actually penetrate into you. It actually typically penetrates down into your fat layers. Usually it gets caught at that point. It will get blocked by like a thin aluminum sheet. Really, any sheet of metal will usually work. Okay? Gamma rays will pass all the way through sheets of metal, steel, whatever, and you need lead coatings to stop gamma rays. Okay, and so you actually need a pretty decent sized lead barrier. It's not like any lead coating will do. Right. If you're talking about concrete, you actually typically need like several feet of concrete to stop gamma rays. Neutrons will pass through most things, and you need like very thick concrete walls. Usually it's something on the order of several meters of concrete or earth. Okay. And then usually what they do to cut down on that amount of space is they put like steel plates every now and then, and they'll put like lead coatings. Yeah. So it's very, very difficult to stop most neutron sources. You need some pretty bulky walls. That's actually where you're getting like nuclear reactors and those thick concrete barriers. That's what you're looking at.
Don't we have some of those built around the Earth specifically to detect,
We do.
like, star
Cosmic particles.
explosions?
So in a supernova, it super energizes these neutrons coming off.
Mhm.
They're called cosmic particles.
Mhm.
And those can pass all the way through the planet, actually.
Right. And that's what we're trying to detect.
We are. And other particles, too. There's some high energy particles that they think might exist. They haven't detected them yet. But they have a little bit of evidence that maybe it might be a thing. Yeah. They're trying to do things like gravitons, and which probably is not a thing, but it's still worth doing. Like, we got to disprove it before we can say anything. That's how science works, by the way, folks. Okay, this is the different radiations and protective shieldings. So how much radiation exposure is too much radiation? So the measurement is going to be the sievert for the SI unit scale. This is SV. This is going to be used to measure the effect of the biological damage. Your average annual dose is going to be 6.2 millisieverts. And remember that millisievert would be 1,000th of a sievert, right? Okay. Now, one of the things to keep in mind here is that we are constantly exposed to radiation. Okay? The potassium in our bodies, there is a certain amount of it that's radioactive. Okay? So just because we need potassium in our diet, we're radioactive. Now, beyond that, we also have the radiation coming down at us from the sun. Okay? And then on top of that, we also have radiation coming from the core of the planet. Does anybody know what causes the planet to be hot inside?
Pressure, friction, gravity.
So all of those would have cooled down by now if they were the sources of heat.
Okay.
So they do contribute to make it much more efficient at containing that heat. And so like it builds up the heat much better. It's like a really good thermal thermal
Insulated.
containment. Yeah, man, I've been sick and I'm still out of it. Oh man. Okay, and I really need like a Kleenex or something. But okay, and so what is the source of that energy? It is nuclear radiation. Yeah. So you actually have radioactive isotopes that are at the center of the planet. Their decay is actually what heats up the planet. Yeah. And so them breaking down actually is what releases things like radon. Has anybody heard of radon before? Radon gas, radioactive gas comes out of the earth because radioactive decay is happening in the earth, creating it. Okay. So we actually have a constant source of radiation that just is for existing. If you go up on a mountain, you'll actually get a larger dose of radiation because you have less atmosphere to block it. Or if you go into a basement in Tennessee that doesn't have a lot of fans.
Lots of radon.
Yep.
Or take an airplane ride.
That's true. You get a extra dose for taking an airplane ride as well. 1 millirem is going to be equal to 1/100,000th of a sievert. So again, keep in mind, we have lots of different radiation sources we're affected by in a given year. Now, the human exposure to radiation has increased by about 40% since the 1980s. There hasn't really been any correlation, though, or any evidence that that's increasing our risks of cancer. And on the other side, we're living longer because of the medical procedures that are causing those radiation exposures. So that's probably worth the trade-off. But we have increased our radiation exposure by about 40% for an average person. Now let's talk a bit about radiation sickness. The effects of radiation exposure, again, dependent on two main things, are we have time and dose. So you can have a long-term exposure, and if it's very low dose, it won't really have much of an effect. Okay? You could have a very short exposure, but if you have a really large dose, you're going to have a big effect. Okay? So long-term exposure at low levels of radiation, typically not as life-threatening as short, intense doses of radiation are. And so one of the only places we've seen a huge effect on cancer levels in terms of people dying from cancer because they've had radiation exposure is actually do you guys know what the elephant foot is? Okay, you're aware of there was a nuclear reactor that melted down in Russia, right? Technically Ukraine, but way back in the Soviet Union era. Okay, that was directly under the reactor. It melted down into a big quagmire of nuclear materials. It's called the elephant's foot. Okay, and the people that were actually working within a meter or two of that, those people actually had cancer from radiation and stuff. They had very highly increased cancer rates. The people that were in the valley at the time of that meltdown, they had a slight increase in thyroid cancers, and which is the most easily treated one. So it actually didn't really affect much. Yeah. So surprisingly, even that one didn't have a huge effect. That was probably the worst nuclear disaster of all time, by the way. So cell types that divide rapidly are going to be killed off more quickly than the other ones. So typically the ones that you really have effects on are like your bone marrows. And that has far-reaching effects on almost everything. So your bone marrows do a lot more than you probably think of. First off, like you were saying before, blood, right? It's where your blood's being produced. It also, though, helps produce parts of your immune system. And then it also has a lot of your stem cells. And so you have a very high likelihood of having some form of cancer. Okay? And there's quite a few varieties of cancer you can get from that. So it's quite a grab bag of stuff. Right? So if you have one place you don't want to have exposed to radiation, it's your bone marrow. Okay? After that would be key organs, especially like your stem cells that are helping to grow those. Okay. Okay, so let's talk about the clinical effects. These are going to be exposure levels in millirem. Remember millirem right down here, 1/100th of a sievert. Okay. So if you're 5,000 to 20,000, can't detect any effect. Okay. Maybe if you're up at 20,000 for a long time, maybe you'll probably have a bit of an increased rate of cancer. Most likely, according to what we've seen, thyroid cancer, which is the most easily treated. But this would be where you'd start actually seeing like long-term effects, maybe. Okay. Under 5,000, there's just nothing. You're gonna get like a 5,000, 4,000s, less than that doses, depending on where you're on the planet. So there's just nothing. 20,000 to 50,000, you're going to have a temporary decrease in white blood cells. And so that's where you're starting to have effects on the bone marrow, like we were talking about. 50,000 to 100,000, you're going to have mild radiation sickness. So large decrease in white blood cells, nausea, vomiting. And this is what we start typically calling that radiation sickness, right? 100,000 to 200,000, this can be light radiation poisoning. So you're going to have a delayed appearance of your appetite loss, nausea, diarrhea, hair loss, spontaneous abortion in pregnant women, and typically you can recover within about 3 months. And there usually is not any long-term effects other than the abortion if you're pregnant. Yeah. 200,000 to 300,000, this is moderate radiation poisoning. So this can be hair loss, fatigue, general illness. Permanent sterility is possible, though not all the subjects will be sterile. Recovery usually takes several months, and you usually end up with long-term effects. Okay, you're almost certainly going to have something long-term. 300,000 to 400,000. Does anybody know what an LD50 is? So that's a lethal dose for 50% of the population. Okay, so if like we were to expose this room to that level of radiation, 50% of us would die.
Is that based on like body mass? Like a bigger person could tolerate more?
So it's, yes, that's part of it, but it's based on a lot of things. So like body mass, how well your body handles damage to its DNA.
Sure. So maybe my overall metabolic health then?
Yeah, your overall metabolic health will give you more resistance. So it gets extremely complicated on who's actually going to survive this, but overall 50% would die.
So would it be safe to say that babies, old, people with underlying chronic ailments,
They're more
would be
likely.
within that 50% that this would be a lethal dose?
They'll be more likely to be
But
within that
maybe
50%.
the Olympian's going to be like, yeah, you're good.
They'll be less likely to be within that 50% that dies.
Mm-hmm.
But again, there's other factors that are not just your health.
Okay.
For example, my grandfather smoked his entire life, went to prison multiple times, terrible lifestyle.
Mm-hmm.
Lived to 98, never had cancer.
Mm-hmm. Okay.
And so highly resistant to cancer of any type, right? Terrible lifestyle. And so some people are very resistant to cancer.
Mm-hmm.
And there's a whole series of events that have to go right for that. Usually it has to do with how well your system that double checks your DNA works,
Mm-hmm.
which kind of has nothing to do with anything else. So, how is nuclear decay equations written? So this right here is actually the breakdown of uranium, a very common nuclear decay that happens on the planet. This is uranium-238. That's your reactant. This is going to be your products over here. So in this case, we have thorium-234, and we have helium-4. Okay. Now, notice that in a nuclear reaction, there's only really two things you have to double check and look at. Okay. All the masses have to add together so that both sides of this reaction are the same. So we have a mass of 238 over here. Over here, we have 234 plus 4, right? Which is 238. All the charges have to add up to be the same on both sides. Right here, we have a charge that would be 92. That's 92 protons, so positive 92, right? Over here, we have a 90 plus a 2. And so that's going to give us 92 again, right? This works even if we end up with like an electron or something, a negative charge. You just add them up, and they have to be the same on both sides. Okay. Now note that this makes these really easy to do. Really, really easy. And that's because these symbols are just that right there, aren't they? So if we didn't know the symbol, what would we do? Well, we'd go to 92 on the periodic table, and that's the symbol. Okay. If we have the symbol, we automatically know this number, don't we? Look the symbol up, grab the number from the periodic table. And then these are just the mass numbers up here. Okay. Anybody have any questions about how to read that or how to balance that out? Okay. Note that it's always really, really, really simple. If you have a coefficient, it would be like right there. So if we had 3 heliums, we'd put a 3 there.
But that's how we would balance it, is by putting in coefficients.
If you have to balance it, yes. Normally, you don't need to balance them though.
Wasn't that part of our homework, was balancing radioactive equations?
Mhm. Yeah. Normally, you're given like, what would this be here? So you're given this plus this, and then this one's blank. And you have to figure out the masses and the charges.
And it would just be determining whether it would be an alpha, beta, gamma particle. That's
All you have to do is just, this is 238. The difference between 238 and 234 is 4. This is 92 over here. Difference between 90 and 92 is 2. Yeah, they're one of those things that once you get the trick down, it's super easy. Most of I don't think I have given you any problems where you actually have to balance them using coefficients. But you might see 3 neutrons. That'd be an example of something you might see. Uranium decay. This is actually an alpha particle decay right here. This is the overall steps, but that's exactly what I had mentioned when we were talking about them right there. Okay, so there's beta decay and positron emissions. So in beta decay, you're releasing an electron from your nucleus at tremendous speeds. And so what you'll see is that's actually the process of going from a neutron in your nucleus to a proton. So you're removing a negative charge that will leave a positive charge. Okay. The positron is essentially the opposite. So you're going to go from a proton to a neutron in that nucleus. So you're emitting the positive charge. The gamma decay, this is going to be that nucleus settling down into a lower energy state. So here we see a technetium, and that's 99M. See that little M right there is actually telling us it's a high energy state one. Okay. And so we emit a gamma ray, and we go to the low energy state one, which is just the 99 TC. Notice the mass and charge, no change. Okay, because this is 0, 0, right? So they have to add up to be the same on both sides. Okay. By the way, you do actually lose a very tiny amount of mass. Okay, so going from here to here, you would lose an extremely small amount of mass to create this energy here. Right?
So because it gets utilized in the reaction?
Yeah, so this is actually kind of an addendum to you cannot create or destroy mass, you cannot create or destroy energy. Energy and mass are actually directly related. Mm-hmm. And so you can actually convert mass to energy and vice versa, technically. Okay, but they're such small numbers that they're never going to be written in this. They would be, 5 decimal places, 6 decimal places down at minimum. Okay. And so you never see them in the 99s here, 100s here. Yeah. And for the most part, most of you don't even need to know that. But anybody ever seen E equals MC squared as in Einstein? That's actually that relationship. Yeah. That's why nuclear bombs make big booms. Is they actually convert like micrograms of their matter into energy. And that's a huge amount of energy. Okay. This is going to be how you produce radioactive isotopes. So again, radioisotopes do occur in nature, but we actually prepare many more in chemical laboratories, or sometimes it's just too difficult to concentrate on them from nature. It's not worth it. And so we just prep those even if we can't find them in nature. Radioisotopes can be prepared by bombarding stable isotopes with fast moving particles, usually an alpha particle, a proton, or a neutron. If it's like a beta particle, it just doesn't have enough mass to actually accomplish anything. Okay, it's too light. So the ionizing radiation is going to appear on the reactant side of your equation because we're bombarding it with it, right? And so we're putting those two things together. Okay, and so right here we actually see an example. 98 MO being bombarded by a neutron. And so that neutron hits that nucleus, ends up fused to it, and we end up with 99 MO right there. Notice the same rules are true as before. So this plus this, 99, that gives you 99 there, right? This plus this gives you 42. So that's 42 right there. Okay. And that's how that works for all those. Now, it can fuse to the nucleus. Sometimes, though, it will cause the nucleus to actually break apart because it'll be so unstable together. All right, so let's talk about some radioactive units. How do we measure this radioactivity? So the radioactivity present in a given isotope is going to be measured as the number of radioactive emissions, typically called disintegrations, that occur within a second. So how many of those break apart per second? Okay, so in this case, it'd be how many times this happens per second. Right? Or in this case, up here, it'd be how many times this process happens per second. And that's called a disintegration. Okay. All right. So the disintegrations per second, this is actually just straight up called Curie. So you know Marie Curie? Everybody's kind of aware of her. If you want a really good biography, by the way, she's a great one. Okay, really interesting individual. Worked with her husband in her early career. Her husband died and then went off on her own in a time where female scientists were not really a thing. So she's a kind of an amazing individual. Really neat. She was a Polish scientist, though she ended up studying radioactivity in France. And she was a peer with Henry Becquerel. They worked together pretty extensively, actually. And so fascinating individual right there. So the SI unit is actually called the Becquerel, BQ. This one's named after Henry Becquerel. And so they are the two units of radiation that measure the activity of that radiation, how fast it happens. Your activity of an isotope is going to define how quickly or slowly it emits radiation. This right here is a summary of those units. And here we see the Becquerel, 1 disintegration per second. The Curie is actually 3.7 times 10 to the 10th radiation disintegrations per second. Okay, half-life. Every radioisotope emits radiation at a different rate. We still have 2 minutes, by the way, folks. Every radioactive isotope emits radiation at a different rate. Unstable isotopes are going to emit radiation faster. The more unstable it is, the faster it emits radiation. If it's more stable, it's going to emit more slowly. So the rate of decay is going to be measured as a half-life. The half-life is the time it takes for half of your sample to decay. Okay? So 1/2 being 50%, of course. So this is also known as the physical half-life if you have to start talking about them in terms of biological elimination. Okay? So that's the physical half-life. The rate of elimination of a radioactive source from the body is the radioactive half-life. It's the physical half-life plus your body actually removing it, as in like urinating in feces, okay? Or shedding skin cells or whatever. Right. So whenever you're looking at medical isotopes, these two things actually become very important to get together. And so this is going to give you, in medical situations, an effective half-life, okay? And that's how long that isotope will be available in that person's body, okay? So remember that the biological half-life shortens the physical half-life, and it's going to give you the effective half-life. Now, decay is going to measure typically with a Geiger counter. That's a little wand thing that goes click, 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 click that you've seen on the movies. I'm not going to go into how they work too much because it's actually kind of complicated in the fact that there's multiple different types now that you probably have thought are Geiger counters. Okay. But essentially what it does is radiation hits that wand. It causes ionization. The ionization causes little voltage spikes. And those are what you're hearing with the click, click, click on a speaker. And they're also what's being measured in the dial. Okay. Okay. We'll pick up here next time. You all have a great day. I will see you next time.
We pick it up in sound because you said that it's mostly radio waves, so that's why they make that noise. It's just kind of like a little radio.
So in a